Okay, so my name is Hansang. I've been in network space, I don't know, 15, 20 years, I guess. And my background is I work for Citigroup today. I'm in charge of both the performance engineering group that looks at problem traces, application issues, network issues, etc. We're network focused. I'm sorry? So we're network focused, but we're always helping application folks with issues as well. So network is kind of the glue that holds everything together. So naturally the troubleshooting group or problems tend to get escalated to network engineering, and we address them. So my background, how I got started was that, by the way, it's a tough act to call as a keynote speaker, but I'll do my best. And so I got started kind of the same way that, there weren't a whole lot of tools back then. Before Network General, there was a product called Spider and Spider Analyzer. And when I first looked at it, I said, wow, this is the best thing since sliced bread. It would help me do all kinds of troubleshooting, but not a whole lot of documentation, not a whole lot of, unless you were deeply in the writing of the protocol itself, material was kind of sparse. So, school of hard knocks, just doing it over and over, probably at the time was the best way to learn. And having a good mentor, doing a lot of research, a lot of reading. So for those of you guys that are just getting started with packet trace analyzing or troubleshooting, my best advice that I can give you is turn on Wireshark, capture all the time, right? And my thing that I used to tell my folks is this: if the first time you see a trace is during a problem, how do you know what's normal? You have no idea what's wrong and what's good, what's bad. Somebody just gave you a packet back in the days of 1,000 packets, 2,000 packets. Today, it's millions of packets in a few seconds, right? And I was telling a story last night during the reading session that there was one trace where literally half a second was worth about 100,000 packets, right? So when they said the problem happened around 12:30, 12:35, and you sit there and you look at the volume of data, and it's like, oh no. So what did I do? We had to divvy it up. Right? We had to chop up a few seconds worth, give it to the team members, and say, deep dive, see if you can find it. And we did, but it was painful. So the scale of troubleshooting is much bigger now, but the fundamentals are the same. So I want to get started. So anyway, the Citigroup background, it's a very large network, and the question that I asked to the keynote speaker was that every NetFlow collector we try dies all the time. And my mission this year is I want NetFlow on every single WAN router in Citigroup. There's one vendor that we looked at that seems promising, so we'll pursue it, but I'm not very hopeful. So anyway, that's the background, and just the size of the network: 300,000 users, about 30 to 40,000 routers and switches deployed globally, about 65% in North America. So it's a big network. So the challenge isn't, the network isn't really a challenge to design. I mean, everybody builds the network about the same way, right? Everybody sees the two circles, the crisscross, two switch. It's the same thing. What the challenge comes from the size and the volume that you're dealing with, right? So no one sees this type of OSPF bug unless you have 2, 3, 4, 5,000 routers participating in the domain. No one has a BGP problem until you put 600 peering rules on a 6509. So the size makes it difficult. The actual engineering of it is just do whatever you're doing and do a lot more of it. Right? That's really the problem. So I kind of wanted to see if anybody had traces that we could look at also. Okay, here we go. So the first slide, most of you guys, by the way, most of you are network engineering, I take it, right? More or less? Predominant? Okay. I hear this a lot. There's a problem, and and the email thread that I get, and the inside joke at Citigroup is I change the thread on the email screen. So I'll get an email saying, we have a network issue, please help us address it, blah, blah, blah. In my reply, I'll say, we have an application issue, and I'll help you with it, right? So the thread wars is my little inside joke. Some people pick up on it, some people don't. So here's a problem that got escalated. This is a very important database used by regulators, used by the CEO of the company to deal with the regulators, etc. So the database itself is just an Oracle database, no big deal. But the report that gets, that it produces goes to the executive management boards, etc. Right? So a lot of visibility. So when they had an issue where all of a sudden the report wasn't working, it got escalated to us quickly. And so, the first thing I want to ask is, as troubleshooters, someone says, this is slow, right? This report producing, this throughput is slow. What are some of the first things that you should look at? Think about, right? I'm sorry?
What changed?
Okay, what changed is a perfect answer. And it sounds like an easy question, but when you have 60 people on a conference call, difficult to nail down. But that's one of the key things that you have to nail down, right? What changed and how did it change? Okay. Now that's not a very technical track. Everybody wants to dig in and look at Wireshark traces, etc. But sometimes, its simple answer is, yeah, there was a change done to database XYZ, and that's the first place you should start. What are some of the other things from a network standpoint that you can look at? And again, the whole point of this course is learn to recognize patterns, right? Learn to pick up troubleshooting tips that you can apply to every single troubleshooting sessions. So, throughput issue. What's the first thing that you should think about?
Physical error.
Physical errors produced by bad links or the bane of my existence, duplex mismatches, right? And this is brought on by the industry when auto negotiation at FAST didn't work quite reliably among different vendors. Everybody hard-coded. Now auto is almost recommended and required for GDE. So we have duplex mismatches everywhere, right? Okay, so once you rule out duplex mismatch, what are some of the other things that can impact throughput? It's TCP course, so what are some of the things in TCP?
Latency.
Latency, exactly, okay. And what else? Retransmissions caused by errors, okay. And I have some examples of that. What else?
MSS, window sizes.
Window size. So window size is a key one, and it's an easy one to look at, right? And we'll look at the trace and figure out how we can do that. So the idea of, how they say move up the layer 1, 2, and 3, it always works, right? So first rule out the physical and stupid things. Duplex mismatches, right? You'll be surprised how many there are out there. In one recent survey that I did for one of our regions, I had 20 to 30% of end user ports that had duplex mismatches. And these things add up. Right? People call with mysterious slowness. Some people get fed up and they call, some people don't. So it's kind of like the scourge of networking, I guess, at this point. So let's take a look at. So let's take a look at this trace file. I know everybody wants to dig right in. And so most of my traces throughout the whole all three sessions that I'm holding, 192.168 is the client, and 10. Is the server. Okay, so you can get an idea of what's happening here. So someone mentioned the window size, right? So when can we see that TCP window size? When is it exposed? The handshake. So here's the handshake, SYN, SYNAC, right? But if I click on any packet, I do see the window size right here, right? So what's so special about the handshake? Scaling, right? So if you're not familiar, there's a phenomenon called long fat network, right? And if you look up RFC 1323, it deals with that. And all that is TCP was born when networks didn't really have this, high capacity bandwidth circuits going long distances, right? So as a result, TCP is not in the best position to maximize long fat networks, right? So anytime someone mentions, oh yeah, I get great throughput when it's close by, but now that it's in a data center a few states over, throughput stinks. You can almost be 80% sure it's a long fat network problem. Very easy to solve, right? You just turn on window scaling, and you can Google it. I don't have to explain the tidbits on how you do that. But in this case, that wasn't the problem, right? So I looked at it and I said, all right, so is it a window scaling problem? Turns out it's not, right? So
what are some of the other things that affect throughput? By the way, everybody, I think someone mentioned window sizes, right? There are two different types of window sizes. They are send and receive window size, right? Receive window size is easy, right? Every server or client constantly advertises its window size. Okay? Is this the send or the receive window size? Receive. Can you see the send window size? No. But what is it typically?
Typically, it's the other side, it's the other guy's receiver.
Right, but I mean, how do you derive the send window?
By observing the flight data.
You can, but you got to be careful because the receiver is the gating factor, right? So the receiver can gate how much you can send, but kind of the rule of thumb answer is receive window, send window, the same, right? And in fact, in like AIX, you'll note that you can't even make the window size to 2 meg because it has an artificial choke where if you set it to 1 meg, it needs another meg for the send buffer, so you can't set it to 2 because you can't go 2 and 2, so it's just 1 and 1. So when you see the receive window size, typically on most OSs, the send window size is about the same. Very few times do you have to worry about the send window, and I have some traces that goes over that situation, but mostly it's the receiver that's going to say, whoa, slow down, I can't consume this data, right? So let's take a look at, so we ruled out the window size, etc. So we're looking at this trace file, and again, you need to develop troubleshooting techniques. The first thing I wanted to comment on is, look at the columns that I have. Everybody has their own columns, right? What's important is to put it in the same position, right? The delta and length, to me, are very important, okay? So why should you put the columns in the same format and use these column definitions to your benefit? Because the human eye is very good at picking up little nuanced changes, even though you're rapidly flipping through the protocol, okay? I'm a huge baseball fan, and I want to, it's applicable. So I was listening to Paul O'Neill. He's a huge, if you're a Reds fan or Yankees fan, you know who Paul O'Neill is. He's a great hitter. But he was commenting during a broadcast that he was walking by the batting cage, and they were pitching about 40, 50 miles an hour, and he couldn't pick up the seams of the baseball anymore. So he couldn't pick up the rotation, which meant that he couldn't discern a breaking ball from a fastball, so obviously he's not going to be a good hitter anymore. And they jokingly said, oh, it's your age, you're getting older. But he said, no, it's just being out of practice, right? And it's the reason why I bring that up is, if you look at a trace file for the first time, there's a lot of information here, right? Just like the keynote speaker said, most of it doesn't really change. So when you scroll through this, your brain will be very good at picking up little hints of where things are going wrong, okay? So within 5 seconds, it should be very clear why this transfer is slow. Why is it?
Packet size.
Packet size? Wrong answer.
The delta it's a chatty conversation.
Yeah, that's it. It's not the packet size that's the problem, right? Because, I mean, unless you're using jumbo frames, 1500 is all you're going to send, right? 1460 for TCP data. So, yes, the packet size is slow, I mean, small, and it is a problem, but that's not the root cause of your problem, right? It's the chattiness of this protocol. So what's happening here, right? The client sends 17 bytes of data. Okay, so this is the application level data. And the server responds with about 362 bytes worth of data. Okay? And you send it again, and you get a reply back. What's the delta here?
30 to 40 milliseconds.
30 to 40 milliseconds. Okay? Because I work with network engineering, I can tell you that this is going to go from New York to Texas. Because that's my delta, round-trip delta, for my 2 data centers in New York and Texas. Right? So without even looking at, I anonymized the IP addresses here, but without even looking at the trace, I know, I'm pretty sure that this is New York to Texas. Okay? Southwest, what we call Southwest Data Center. So the problem is that every time you ask for something, you have to get an answer back. right? Very typical chattiness. So what happens when they were in the same data center? What is the delay between the send and the receive when you're on the same LAN segment?
Milliseconds, maybe less.
Microseconds, right? In a modern network, you're talking microseconds, right? 1 millisecond doesn't even come into the picture with modern switching fabric. So now you made it an order of magnitude longer, and if you're doing hundreds of thousands of these queries, your report time just went from 10 minutes to 10, 12, 13, 14, 24 hours. And it's actually easy math to do, right? So if you want some homework assignment, kind of think about how do you measure that out, right? There are programs like OpNet that can instantly tell you what it is, but in this case, it's simple math, okay? How many round trips is it making? So when I talked to the developer, who was very adamant that it was a network problem, because nothing had changed, and then to your point, we kept talking about what changed, and he said, oh yeah, by the way, last week we migrated some servers. I said, did you migrate to Texas? And they said, yeah, how did you know? I said, well, because packets don't lie, right? So when we looked at the trace, I said, what is it that you're doing? Now, this is a key point, so it's not a technical point, but it's a key point. Not everybody that you're talking to understands TCP. They don't understand chattiness. Well, everybody knows what chattiness means, but they don't know what the ramification of chattiness is. They don't know what the window size problems are. They don't know the packet size issues, retransmissions, etc. Right? So when you talk to someone, put it into a context that they can understand. And a classic example that I gave to this person is, you have 1,000 people you need to move, and you're using a motorcycle to do it. Right? You're putting one passenger on, you're going to and dropping them off, coming back, picking up another person, dropping it off. I said, if you use the bus, you can pick up the whole entire load in one shot, and you're done, right? And then, of course, the follow-up question is, well, I didn't have this problem when they were sitting next to each other. I hear that all the time. That's a network, because when they were close, I didn't have this problem. I said, well, if you only have to go half a block, using a motorcycle isn't too bad, right? Because you can just go back and forth very quickly. The problem is when you lengthen that out, then you have a problem. And then she immediately got it and said, oh, okay, I see what you mean. So that's nice. How can you help me? So when I looked at this query, what's unique about it? Again, keeping in mind that the client address space is 192.168 and the server is 10 dot, right? What is the client doing? And I'm not talking technical terms, but when you look at this,
Receiving data.
receiving data, right? So when in a database, when you're receiving data, what operation is it doing? What kind of query? Select query, right? So almost always in a database, when the client is receiving data, you're doing a select query. You're saying, hey, match these conditions and give me the data, right? It can be a select star. It can be select where certain table name equals this, field, etc. So when you see that, then you have a shot at fixing this. Why?
Optimize the query.
You can optimize the query. Exactly right. Okay? And so I said, oh, are you doing a fetch? He said, yeah. What's your prefetch statement? I don't know. I didn't set it. Well, Oracle's default is extremely low. I think it's 10. Right? What that means is, when you have, pretend this is a database row. Right? So each one of these is a record. Right? And you say, give me this, give me this, give me this, give me this. And what Oracle does is it says, give me this, and the next 10 rows in one shot. Okay? So when you have small amounts of data, you only get 10 rows at a time. Right? So what we did was, okay, so we looked at this trace, and you can see the throughput here is horrible. Okay? And in fact, if you do statistics summary, you can see that the throughput here is 0.052 megabits per second. Okay? And there's a 10 gig network between the two. So, what did I do? We changed the prefetch option in the connection, and this is the same transfer. Notice what happened here, right? When you eyeball it, you can see what?
No.
I'm sorry?
I don't matter.
It's a little better, but why is it better? So now, this is where you need to kick it up to the next notch and start thinking these through, right? Why is it better?
Packet length is with 242.
Packet size, okay. Packet size does come into play somewhat.
2 data per app.
2 data per act. Okay, we're getting warmer, right? So that's kind of like what I call, like you're right there in the middle stages. Now, take it to the next level.
And the application's not fetching a tiny bit of data at once. It's fetching a whole lot of
Yeah.
data and then sending it down to TCP.
Right, but how do we know that?
Because we see you don't see the chattiness anymore. I mean, you're still getting an act between select and max, but you're seeing a whole bunch of data going at once.
Exactly, you're both exactly right. There are no more application level message going back to the data, to the database server. Every one of these acts coming back has length of 0. What does that mean? Application has no play here anymore. You've now taken the application message where you were saying, hey, can I have this? You can have this. Can I have this? You can have this. And you made that to give me all of this and don't bother me until you've given me all of it. So now the application level message is nowhere to be found. This is pure TCP, right? So the key point is, in the previous trace, there were application level messages going back and forth. How do I know that? Because every one of these 71 byte packets had a 17 byte data. I don't know what they are. Well, I know what they are. They were select statements. But I know that it's an application level message, so TCP can't do anything with it, right? So you have this bus that can go 200 miles an hour, but you're only taking 17 passengers at a time, okay? And that bus can't come back until the round trip comes back, and then you ask for more, and then so the bus is going back and forth empty, okay? So the key point isn't here that the packet size is 400. Yeah, it's not good, but technically, if I take the application level message layer out, I can speed up this throughput greatly, even at 400 bytes per packet size, okay? The main point here is that the application level messaging has disappeared, and my throughput went to 25 megabits per second with a single line prefetch size when you're setting up TNS. Okay? And we tried various numbers. We went from default of 10 to 10,000, 20,000, 30,000, 50,000. And at that point, it kind of became like an academic exercise. So my price for helping her was that she helped me with these experimental data so that I could collect them. Okay? Yes?
I'm just curious, do you recommend that to the Oracle DBA?
Yeah.
And how will do it?
So as the best practice for us, we always ask them to increase the prefetch size because there's no real penalty so long as you have the bandwidth. Okay? And in fact, we tune down so that you don't experience exactly what you saw in the keynote, where you have this sudden explosion of data to crash, explosion of data to crash, right? That's a typical sawtooth TCP diagram. So experiment with it, but there's very little downside to making the prefetch. Because if you don't have the data, you're not going to use it anyway. Okay? If there's nothing to prefetch, Oracle doesn't spend time prefetching something that doesn't exist. Okay? So the key point that you need to take away, don't look at the packet size so much. Yes, they're important, but the idea here is that the application now got decoupled from the transfer. Okay? And then, of course, when we did the transfer here, it didn't work, right? And she called me and said, hey, all this thing you told me, it's great, but throughput still sucks. Why did that? I mean, I showed you the 25 megabit throughput, so obviously it's fixed here. But when she first did it, when she first made the prefetch to be 10,000 and 20,000, throughput wasn't that great. Why was that? Why did that happen? Any takers?
She comparing it to local transfer?
No. She was still doing it, same baseline, Texas to New York. So I said that the application was decoupled from TCP in terms of throughput. So what was my problem with TCP? The typical ones that we always talk about. Window size. So if I take a look at here, what's my window size? 25,000. What does that mean? In layman's term, what does a window size mean? And if there's nothing that you get out of this, I want you to get two things out. Application level message interaction. Okay, it's very important because that clues you into the chatting assembly. But what does TCP window size really mean?
The amount of data is allowed to be unacknowledged on the network at any one time.
Say that one more time.
It's the amount of data that can be unacknowledged.
Okay, so
X amount of outstanding data.
okay, so that's an answer. I'll apply that. But to drive home the point, again, when you talk to someone who hasn't read the Comers of the world, Stevens of the world.
Number of seats on the bus.
Number of seats on the bus. Okay, that's good. That's good. Now you can take that to one next level up and say, this is how much you can send in one round trip. That's it. You can send one window size per round trip. That's it. No more, no less. So if you have 25,000 seat bus, in one bus, you can put 25,000 people on it, and you cannot put any more people on it. So your job is to make that bus bigger, okay? So that in one shot, you can send more people. So remember, window size says, in layman's term, you cannot send more than what the window size is per round trip. Okay? At that point, throughput calculations become very elementary. Okay? Because it's this much data per round trip. Do that however many times to transfer the data that you need. Okay. Did everybody get that? That window size? Yes.
Question, this actually came up a few weeks ago. On a Windows box, isn't the maximum like 65 by 35 for the window size? And is there a reason not to just set them all 65 by 35?
So the question is 65535.
Is the maximum window size, I think, right?
Uh-huh.
And then is there a reason not to set the window size so high?
So the reason why you don't want to set it to, so the question is, should you, as a company policy, push out a change for every registry and every stack to increase the window size to 65K? The answer is, it depends. The old consultant answer, right? Actually, I'll take a quick funny segue. My boss told me that, I said, we got a couple of these consultants, which one should I hire? And he said, one with one hand. And I said, what? He said, I want the consultant with just one hand. And I said, what are you talking about? And he said, every consultant says, well, you can do that, but on the other hand, you should do this. Right? So he said, I don't want the guy with two hands, I want the guy with one hand. So the reason why it depends is, if your network can handle the throughput, right, it's you're fine, there's no penalty to it. Except, the only corner case where you have to be careful, every TCP connection requires window size in the memory to handle the guarantee of delivery.
How much RAM, right?
Okay, so if you say your window size could be 2 meg, receive window size could be 2 meg, then you just made it a 4 meg, right? Because you got the receive and send window. So every TCP connection will eat 4 megs of connection. And remember, TCP connections don't die immediately after they close. So when you have internet-facing, customer-facing, that's when you have to be careful. For most corporate intranet type servers, there's very little danger as long as you have the bandwidth. Okay? As a matter of fact, what we do is we don't go to the theoretical maximum. We always set it to about 5 to 10% of the choke point, so that because we have so many servers and clients, we don't want to saturate one guy, okay, with the bandwidth with one person. Okay, any questions on this trace? Okay, yes?
Do you guys implement any time tracer tactics for
Yeah, we
Curious
have.
how it plays in.
Yeah, in fact, in my in the advanced session, I actually have a riverbed trace that we look at because it gets kind of interesting when you have WAN accelerations that munch packets along the path. So yes, we have quite a lot of riverbeds deployed, and we have and it makes troubleshooting a little bit more difficult. But if you know your stuff, the magic kind of disappears, and I actually have a trace that shows that. Okay, and it was actually a problem that we ran into. Okay, so the next case, I'm trying to move along here because what is the session at? 11:30. Okay, so if I pick up the pace here a little bit and you have questions, stop me and ask questions. So the next question is, same thing, I get called, my team gets called and says, the network sucks, what are you guys going to do about it? And I said, all right, let's take a look. Okay. The first point I have is, in the immortal words of Ronald Reagan, trust but verify. Okay. What I mean by that is, even going back to network generals of the world, expert analyzers tend not to be experts sometimes. Okay. They can greatly help you find, kind of shine a big light, searchlight to where it might be the problem, but you can get lost in the weeds trying to address every single problem. So if you spent any amount of time trying to see if that expert diagnosis screen will go to 0, right, you're on a fool's errand. Okay? So let's take a look at this. So I get this trace. And so let's start talking about some of the techniques that I go through. Again, you see my columns, right? And I can quickly look through. And I can make some quick observations about this. Someone obviously messed with the MSS because I don't have full-size TC packets here. May or may not be a problem. Probably doesn't because I can kind of see that they come in bunches, right? What else can I look at? So some of the things that I do. First thing I do, I sort by delta column, and I kind of scan through it to see if anything jumps out. If I have column after column, huge chunks of the same value, it kind of leads me to thinking, well, maybe I got a latency problem here. Okay, so that's one thing that I do. The other thing that I do almost universally every time I open a trace is I'm looking at any flags that Wireshark picked up. Okay, so this is kind of like the poor man's expert analyzer, and I look at it, I put it in, and it took me a long time to find this little feature gem here. And I used to sit here and count these by hand until someone showed me, hey, it's right here, right? I was on a conference call, and the guy said, oh, you got 440 events. I said, how did you count that so fast? Down here. Silly me. So we have 220 of these analysis type events out of 1,600 packets. And what are they? Lost, segment lost, and I said, the first thing I said was, oh man, we got a problem here. What's happening here when you look at this? I'm sorry. Yeah, thanks for stealing my thunder. Okay, but it's packet loss, right? So when you look at this, you're thinking, oh man, I got a packet loss problem here, right? My bandwidth is no good. My links are no good. I may have a duplex mismatch. Right? Duplex mismatch can do this, so we rule that out immediately, right? So, but something caught my eye, and if you go back to my presentation here, I make a thing about here about this guy Malcolm Gladwell, he wrote a book called Links, and another one.
Outliers.
Outliers, I think, is one, and there was another one. Tipping Point, yeah. So they're kind of interesting books. It almost sounds like New Age-ish, kind of foo-foo stuff, but it really isn't. And one of the things in the Blink is he profiles different people. There's a guy who's a coach, tennis coach, and the instant a professional player throws up a ball, he knows that it's going to be a fault. He doesn't know how, but he knows it. Okay? And the thing that I'm trying to say here is develop that talent. How? By looking at traces. And you have to trust your brain to do this. Subconsciously, your brain will learn. It'll learn the patterns of what a normal trace looks like, what an abnormal trace looks like, and something that doesn't quite look right. Okay? So, in this one of my guys on the team was going to punt to, not a lower team, but a team that, like a level 1, level 2, help desk type operations folks to go troubleshoot where the packet loss is occurring. Okay? So when we looked at this, I said, yeah, go ahead. And then I said, well, wait a minute. Something doesn't look right to me. I don't know why, but I said, something doesn't feel right here. Right? And what, anybody see, can anybody pick up something here that, I know it's hard when you're looking at it, but. Yeah. So there was one keyword there that was interesting. What was it? Retransmissions. If you have packet loss, shouldn't you at least see one retransmission? I mean, shouldn't there be, in this analysis, you see the segment loss. Shouldn't you see the word retransmit there somewhere? Right? So at the time I didn't know, because literally after looking at it for a few seconds, I said, gee, something doesn't look right. And then as we were going down, someone said, you notice there's no retransmissions? I said, yeah, you're right. There is no retransmission. So if you have packet loss, what does that mean? It means that someone sent some packets, they got lost, and you had to resend them. Okay? Now, are you guaranteed to see the retransmission all the time? Why or why not? They might get lost, but why would you see them sometimes and why would you not see them?
Depends on your observation point.
I'm sorry?
Depends on your observation point, where you are along the path.
Depends on your observation point. So these are the nuggets that you have to constantly think about as you're analyzing trace files. So if I'm the sender and my analyzer is right here, right, and packet loss occurs over there, I'm going to see retransmissions, right? Because I sent the packet, the analyzer picked it up, it got lost out there in the ether somewhere. Something happens, I retransmit the packet. I now see a retransmission. If I'm sitting on the other side of that cloud, I never saw the first packet, right? So I don't see a retransmission. I'm going to see a missing hole, the sequence numbers going along, and then all of a sudden there's a hole. And then a few seconds later, a few milliseconds later, the straggler shows up. And I can say, yeah, okay, somewhere between this beginning of the table and the end of the table, the packet got lost. If I'm on this side, I see 2 packets. When I'm on the other side, I only see it once. Okay? So the observation point is important. So where are we capturing in this packet? Again, we have 192 client, 10 dot is the server. Looking at the first couple of lines of this trace, where can you?
The server.
The server, which is a 10 dot. Why?
The latency delta.
Explain that for me.
We see the SYNAC go out from the server way too fast to be coming across link. We see the ACK come back from the client way too slow to be coming from, or the capture being on the client.
Yep. So this is another important point. When you're doing trace analysis, always think about these things in the background and make it subconscious where you can pick them up instantly. Okay? Do we know at this point in time, at time 0, where we are in the packet trace, where we're observing the packet trace? We have no idea. All we know is we instantly saw a packet pop out. Okay? I don't know if we're closer to the server. I don't know if we're closer to the client. But the next thing that happens is, okay, I saw this first packet. The second packet happened 500 microseconds later. So I can reasonably conclude that I must be close to the SYNAC guy. Right? Because typically, SYNAC doesn't have an application delay penalty. Right? That's a stack behavior. Very low level, happens very fast. So SYNAC is one way to find out where you are capturing. Okay? And obviously the ACK that has to come back is about 34 milliseconds away. Okay? So now I know I'm capturing near the server. Okay, so that's good. Mentally file that away. Who's doing the sending? Server. And I'm capturing near the server. So should I or should I not reasonably see retransmissions? Am I on this side of the table? Or am I on the other side of that table? I'm on the near side. I'm closer to the transmitter. Okay? And if I'm closer to the transmitter, it stands to reason that I should see some retransmissions. Right? Because if the packet loss is occurring over here or out there, I should see some retransmissions. And I don't see that. So these are things that happen subconsciously almost, so that when I looked at this trace, I said, something's not right. Right? And then as we delve into it, and you go through this analysis, you're like, everybody keeps saying, oh yeah, you're right. Right? So then someone said, oh, no retransmission. So let's take a look here real quick. And as I'm scrolling through this, and you're thinking, oh man, there's all kinds of loss, etc. What's another thing that jumps out at you as you scroll through this? Anything else jump out? Deltas? Okay, that's one. What else? Things that are important to performance.
Session gets torn down.
Session gets torn down. How do we know that? Because we see a lot of SYN and FINs. Okay? So let's check that. Why am I doing flags equals 0, 2? Because that gives me just the sins. And I get a quick count that there are 102. Again, I used to count. And then I thought I was really smart because then I would go page at a time, and I knew that in the page there were like 16. I'm really optimizing my workflow here. So it's 102 packets, 102 TCP connections. Why does that matter? Because every TCP connection has penalties. What are some of the penalties associated with the new TCP connection setup? During the keynote, slow start. Right? Is it slow start? So every TCP ramps up slowly. So if you have this much data to send, you could do it in one shot. But TCP says, no, 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 you can't do that. You got to ramp up. Oh, I'm finished. Let's tear this down. Let's open the next connection. I can send this instantly. No, 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 you can't do that. You got to ramp up slowly. Okay, so there's some penalties to TCP slow start, but it's a safeguard. So we look at that and we think, okay, there could be some problems here with a lot of TCP connections happening. Okay, so this is a, and you can say or TCP.flags so it's 12, for example. Right? Or you can have another TCP buffer that only looks at, I don't know how to do it in a display filter without typing out the whole thing, but in the TCP dump, you can look at TCP header offset 13, and you can do quick and binary math to look at every single TCP handshaking event. Send, SYNAC, reset, FIN, FINAX. Okay? And that's a good TCP dump trace. TCP dump or capture filter, because if you're looking at just setup information, you don't need all the data in between. That's a good way to capture it. So let's look at, so I'm going to go to a particular packet here that I marked. And let's follow this TCP trace. Okay. So here it says, we're looking at the traces here. So we got the send SYNAC. Segment lost. Right? It says here, segment is lost. I'm looking for 2401. Right? And here's the ACK number, 2401. So let's go back. So when you see that, go back a few packets, and when you're troubleshooting, this is a key point. Find out if both systems have caught up or not. What do I mean by that? Are there any unacknowledged data that's outstanding? Okay? So let's take a look at that real quick. So up here, I look at this packet here, and he says sequence number is 1. And by the way, I'm using relative sequence numbers. And I just sent 557 bytes of data. So my next expected sequence number is 558. This is where I'm going to pick up the next time I send you something. Okay? It also happens to be, just like the keynote speaker said, it's also the ACK number on the other side. And what is my ACK number here? 558. From this 10 dot perspective, are we all caught up? Yeah. Because my acknowledgement was for the previous sender worth of data. The sender said, I'm going to send you 557 bytes of data, and the next byte that I send you is going to start from 558. And so when the receiver says, okay, I'm good up to 558, 557. I expect you to send me 558 next time, so we're all caught up. Okay? Then look what happens to the client. Why? His sequence number starts at 558, right? So there's a couple things going on here. This is a duplex analysis, meaning you have to look at sequence numbers in both directions. When I first start teaching TCP, I always say do unidirectional analysis first. Look at one side of the conversation. But in TCP, both sides can be sending and receiving at the same time. So this is one of those cases. So my sequence number is going to be 558. That's what I'm going to send you next. So if I come over here, what's my sequence number? 558. Have I sent any data? No. It's just an acknowledgement. What does that mean? What happened between here and here? Am I sending any data to the server? No. Have I received any data from the server?
Yes.
Yeah, how do I know that?
2401 acknowledgement.
Yeah, so all of a sudden, between here, where my acknowledgement is nothing, right? I haven't started receiving anything from you, to all of a sudden my acknowledgement number is 2401. So the client, 192.168 guy is saying, the next packet you send me should start with 2401, sequence number. Have we seen those packets? No, we haven't. So somewhere between packet number 118 and 119, 2,400 bytes or so of packet data went across without us seeing it. So is that packet loss? Yes? Maybe? Maybe not. I don't know at this point. Right? It's easy when someone's presenting. The answer's there. Right? They always give you. But if you're like most college courses, it's left up to the reader. Phrases that I hate most. Or it can be easily seen. And it's never easily seen. So I can come up here and say, oh, it can be easily seen that it doesn't work that way. Keep open trace files and look at them. And always think. Don't just look. Always think about what it means. Because if you know what it means, you can derive a lot more information from packet traces. Yes, go ahead.
Are you actually capturing on 10, 10, 10, 10?
Near the 10, 10, 10.
Not on it.
Not on it. Okay? And there are some ways to find out if that's the case or not, but that's for another time. So what happened here? What's the likely source? Mentioned it earlier. Stole my thunder. It was close. So you're overrunning the TCP dump buffer. Yeah, possible. The other one is span session. So when I went back to look at the span, and the span is Cisco switch can mirror another port to the analyzer, what happened was they created a default transmit and receive span to another port. So if I have a 100 megabit server that's busy receiving and sending, I could theoretically have 200 megabits worth of information, right? 100 megabits sending, 100 megabits receiving. Now you take both of that stream, put it to a 100 megabit port, outbound, you're bound to overrun. So when I did a show port, sure enough, a lot of discards on the span port. Meaning, I never saw, there was no retransmissions here. There's no packet loss. It's just the analyzer thinks it is because analyzer didn't see it. One way to, how would you find this? How do you find a retransmission? What's one good way of doing that? You can do that. What's another way? TCP.seq equal. Okay? You're looking for a TCP sequence number. And then whatever that number is you're looking for. Okay? If there's a retransmission, you should see two of these. Because the sequence number has to start at the same. Okay? So if we see a retransmission and this was a real sequence number, you're going to see it twice. First, when you sent it out, got lost, I have to retransmit, and the sequence number has to be the same. Not always, but in most cases, the sequence numbers have to be the same. Then you know positively you have a retransmission. You positively have packet loss because the sender sent it twice. So when you're doing analysis, don't just put a sniffer out there. After you kind of get a feel for it, if you had the option of sending it, putting it closer to the sender or the receiver, if you have the luxury of doing both, that's great. But if not, think about where you want to place your sniffer. Okay? Where you want to put your probe, because is the sending more important to you or is the receiving more important to you? And the only way you're going to answer that is by doing trace analysis and getting a feel for what's important and what's not. Okay? Any questions about the trust but verify case? Okay.
Your sequence number in there, do you have relative sequence numbers on? Your filter can use relative? If you have
Yes,
relative
absolutely.
off, you
Yep.
have to use the
Yep.
non-relative?
So the relative sequence number carries throughout, including the selective ACK field. So you can use relative sequence numbers. Okay. Now, if you don't use relative sequence numbers, here's what it looks like. See those numbers? It's harder for you to pick up because it's a large number. Okay, so trying to keep track of this sequence number is much more difficult than 1, 2, 20, 2,000, etc. Okay, so use a configuration profile to set it up so that you can quickly go back and forth. There are cases where you want to use real sequence numbers, which we'll get, which I have a case study on. Any questions?
You mentioned that retransmissions positively tell you that you have packet loss. Did you have a TCP issue where it's retransmitting prematurely?
Yeah, as a matter of fact, in the advanced session, I have a case where it's a unidirectional failure, meaning the receive is still happening, but the sending isn't going on. So you can have TCP level issues, you can have driver level issues, but actually, thank you, because it's a perfect segue into my next slide, right? Which is, sometimes it really is a zero. So if you guys heard me speak before, it's a common phrase, and you should, every network person should tattoo this on their forehead, or maybe the coworker's forehead so you can see it. You know, when you hear who's beating, right, think horses, not zebras. So yeah, both animals running makes the same sound, but what are the chances that it's a zebra, right? Almost always it's a horse. So don't go looking for the most exotic answer. But every once in a while you come across a trace where you ruled out everything and there can only be one answer. It's improbable, it probably shouldn't happen, but it happens from time to time. Okay? So it's an FTP transfer. FTP is not working. It's between a financial customer of ours. You know, our managers are getting irate. Program manager, their program managers are getting irate. So it got escalated up. So if it's an FTP problem between two vendors, what's involved? Firewalls. Yeah. What are some of the things that can go wrong with a firewall? Any? Again, if you know TCP, then you kind of have to know FTP, and you have to know how FTP works. And if you don't know how FTP works, this URL that I have in the presentation has a very clear explanation of active versus passive FTP and how it can impact your life. Okay, so I'm not going to go over the key point is that in an active FTP session, the server opens the channel back to me. So I contacted the server, right? I contact the server. The server says, "Hey, I'll talk to you over here." Most firewalls, early firewalls, didn't like that too much because the whole purpose of a firewall is you can have outgoing connections, but people can't just make a connection back to you, right? So then, as firewalls got more intelligent, they understood the concept of FTP and said, "Oh, I see this message you're sending, the port message that you want to negotiate and talk to this port. I'll let you through." Okay, so every time there's an FTP problem, the first thing you look at is firewall rules, see if anything's being dropped, etc. Okay, here that was not the problem. So let's take a quick look. So I chopped off some stuff that's not really required, and it's again Cincinnati. And at this point, is it worth looking at the window sizes? Maybe. Eventually, when I get this to work and the files transfer is going to be big, they're going to call me again anyway, right? So we'll take a look at it. Anything wrong here, 655, it's okay, it's fine, right? It's a good number to start with. Synac, it's fine, okay? But the window size is 16K. So what kind of box is that? Probably the Boulder Solaris. The default is 16, 17K, right? So these are some of the things that you can pick up by looking at the initial window sizes, okay? So we go through the typical user login, passwords required, blah, 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 blah. And so let's do what I normally do. What happened here? Retransmits, right? So what's the likely cause for that? Somewhere out on the internet, packets are getting lost. I'm closer to the sender, so I'm actually seeing retransmissions of the same packet going back and forth. Okay? When you look at a retransmission, something that you should do, okay, is to look at the IP ID. Okay, why should you look at the IP ID of a retransmission?
Well, tell if it's truly the new IP packet that way, or whether any trace uses happen to see the same packet twice.
Yeah. It's a quick way of identifying if someone duplicated that packet for you, or in fact it is a real retransmission. Okay? It's a very common rookie mistake to span the VLAN, or span the inbound and egress at the same time. So from a switch perspective, you see the packet coming in, and then you catch it again as it goes out. It's the same packet, right? You just caught it on the inbound and on an outbound basis. That's going to happen when you capture the VLAN. So one of the quick ways to identify it is, hey, did the MAC address change? No. Did the IP ID change? No. It's a duplicate, get rid of it. Okay? And you can use editcap-D to do that. Editcap-D will say, it looks at plus or minus 5 packets, I think, and if they're similar in characteristics, it'll nuke it. Okay? So editcap-D is a good flag to use. So what happened here? So let's take a look. Okay? So this one is actually interesting, and I hate to blow through it, but let's take a look at this guy. Okay? So it gets interesting right about here. Right? We got a TCP ACK loss segment. So let's kind of back up a little bit and take a look. So here, what do we see? Let's get rid of this IP field. Let's go back to the interesting part, which is the sequence and the acknowledgement number. Okay? So let's back up to the client here. And the client says, okay, my sequence number is 62. I'm sending you 8 bytes of data. So of course, my next sequence number is going to be 70. The next packet that I'm going to send you will be 70 onward. And the server says, okay, my acknowledgement number is 70, so I'm all caught up. And by the way, I'm sending you some stuff, and I'm going from 193 plus 20 for 213. Again, it's a duplex communication here. Okay. So this server 10.10 sent, it says next sequence number is 213. So his acknowledgement number for the next packet should be 213, right? And the acknowledgement is 213. And my sequence number is 70. Okay? So sequence number here is 70. I go back a couple things. It says next sequence number is 70. So far everything looks good. In packet number 13, I'm saying that the next packet I send you will start with 70, and sure enough, the next packet then starts with 70. Okay? And I got 24 bytes that I'm sending, so the next packet that I'm going to send you will start with 94, right? So what should the acknowledgement number be from the other guy, the 10 dot guy? I'm sorry? ACK of. What's the ACK should be? What should the ACK be? 94, right? And this next sequence number is invaluable. I mean, it's kind of a simple math to do, but just being it displayed like that helps troubleshooting considerably. Again, as you look at more and more traces. So the next sequence number is 94, and which means the next packet's acknowledgement should be 94, and I can come over here, and what's my acknowledgement number? What happened? So let's talk this through, right? This is an advanced session. These are things that you should immediately know, but sometimes you get lost with that whole tree for the forest idiom here. In layman's term, what happened? Someone described to me the conversation.
The NAT helper extended the port and got cheap.
I'm sorry?
NAT helper extended the packet.
The NAT helper extended the packet. Okay, some experience there. But what does that mean? If you don't know that, what does it mean from this TCP trace? So within the confines of this trace, what is it saying?
You got 3 extra bytes.
Someone got 3 extra bytes. How do we know that? Because in here, he said, my next sequence number is going to be 94. The next time I talk to you, I'm going to start from 94. Okay? The next time I talk to you, I'm going to start at 94. And all of a sudden, the guy says, all right, the next time you talk to me, you're going to start at 97, right? And you say, no. I didn't say 97, I said 94. I sent you up to 94 bytes of data, and the other guy all of a sudden says, yeah, I'm good till 97, we're good. And you as a sender say, wait a minute, I just said I'm going to start at 94, but you're telling me you got 97. How is that possible? So this isn't packet loss, this is packet creation. Someone added 3 bytes of, and who does that? Is it a router? Yeah, maybe. If you configure NAT on a router, right? Is it a firewall? Yeah, maybe. Do they have a NAT translation somewhere that's adding padding, packets, etc.? Yeah, absolutely. Right? A stupid router, meaning just guys that pump packets from interface to interface, don't do that. They don't touch packets. They just look at the header, they move to the next. But when you configure NAT, network address translation, when you have a firewall that's inspecting packets, when you have intrusion detection that's investigating deep packet analysis for application layer stuff, those are the ones that you need to target. Okay? We never found out the real culprit here because it wasn't us. Right? I know it's but we actually put the sniffer on the clean side and the dirty side, and they were identical. So it happened past us. At that point, I said, "We're done. No problem. Call me when you got it fixed." But it's so we said, "All right," but we helped them out. I almost said the vendor. We helped them out by saying, "Look for a device that's doing NAT, protocol address translation, a firewall, and it's adding 3 bytes." Right? So the next day it disappeared. So they addressed the issue. Okay. So again, if you're looking at Wireshark's thing, it's easy to say, "Oh yeah, something got lost. It's a lost segment." It's easy enough to just dismiss it at that and move on. But and normally with my rule of it's a horse, not a zebra, you would say, "Yeah, okay, something got lost, nothing unusual, nothing exotic, move on." But when you start to just do a quick trust but verify, quick sanity check, this didn't make any sense. Okay? Because the acknowledgement number can't be bigger than what I sent to you so far. It can't. Someone can't just create packets along the way. And in this case, that's exactly what happened.
What would happen is it's not the layer of gateway for everything. When it's just like that the IP address and port number, made up of a different number of digits, adjusts the sequence number on the way back, the way forward. It's obviously not the correct.
Yeah, and if you don't know what he just said means, if you go back to that URL, you're going to see what's called a port command. And that's a way of saying, I want to talk to you on this side channel for the actual transfer. We got this channel set up for the command, so I can tell you what I need. But when you actually send me the data, I want to connect to you over here. Active and passive means that you either initiate the connection or the server initiates the connection. But the bottom line is FTP has a control traffic and data transfer. Okay? And when you have those port commands that change IP addresses, so in other words, when you're translating 192.168.1.1, right, there's 1.1, there's 1 digit there. But if you need to translate to 10.10, you just added more digits, right? Because 1.1 is not 10.10. So some stupid translators can get confused and add bytes because of that reason. Okay?
You mentioned edit cap -D introduced. Does that look at data?
No, it actually looks at identification, MAC address, I believe, and a couple of safe ones.
Could you intentionally manipulate retransmits to hide data at a stream level?
To hide retransmissions?
To cover data that you've already sent. If you send a retransmit to different data.
No, because when you retransmit, what's going to be different? It's a new packet that the server has to create. IP ID is going to be different.
Sending the same IP ID, sending the same byte link, could you cover covert data? Could you send data to an exact aggregate payload, cover the data out? And how would application level firewalls, IDSs, everything else respond to that?
So, okay, but I need to know how you're creating this and what you're changing or not changing.
So if you control the stack,
right,
you can send a second identical packet with different payload, exact same ID, exact same data link, and actually cover over a segment of data. So if you control the stack on both sides, you can actually send a covert message using.
Okay, so you send ABC, now you're sending 1, 2, 3.
Exactly. So
okay.
It's a way to, if you're looking at pure resessionization, at an application level for IPS or certain application level firewalls, they'll actually buffer a couple of packets before they do
that.
In case they need to span data segment.
Yeah, in that case, it's considered a retransmission from a TCP level, but the data can be different. Right? Edit cap -D doesn't come into play there so much because the IP, but if you're manipulating the IP, yeah, you can do that now. If you're on the other side and you're receiving that information, you're going to need special parsers to get that out. But if you have complete control of the servers, then everything, you've lost the war anyway. Right? So the answer is yes, you can hide packets that way.
So we're starting to see some malware do that,
Right.
potentially to send out small messages. What's interesting is you don't need to control both sides. All you need is a snipping location somewhere along the line. So if you're watching that transmission, you can actually pull out the first packets and get the data you need.
Right.
And most stacks will ignore it. Most stacks will do it.
Right. Right. You're right, because it's a way of hiding in plain sight, basically, right? So the one, again, key points, right? You have to kind of understand how FTP works. You have to trust but verify. And every once in a while, you're going to get a real head scratcher and say, oh, wait a minute, this isn't a normal 99% case rates packet loss, this is packet creation. Okay? And that's the same here. You rule out all impossibles, and however improbable, whatever remains is the answer. Okay? Any questions about that? Okay, so the next one is it's a common topic that comes up, right? Again, we have a software that updates patches and whatnot to 300,000 desktops. So again, everybody does it, but the volume makes it a little bit more challenging and difficult, keeping it all in sync. So you have all these staging servers that, you know, per region, per large buildings, per AS, etc., whatever the criteria is, they have all these staging servers that get all the same patches, and then when you log in, you get the same types of patch. That transfer between the systems where their staging area is slow. It became slow. So they contacted our group and said, look, this transfer is slow. We think it's a network. And again, that went to the threat world, you know, network issues, turning back to application issues. So what's the usual suspect? Again, duplex, window size, packet loss, long fat network. Always think about those things when there's a throughput issue. You can quickly rule these things out. Okay? You can positively rule out a window size issue if you caught the Cincinnati. You can't do Windows TCP window analysis without the Cincinnati because you don't know if it's being scaled or not. Okay? So Cincinnati is very important. So when you're troubleshooting and doing packet capture, ask the person to completely get out of the program before capturing. Because if you start late, you don't have the handshake and you don't know if they're Windows scaling or not. Okay? Duplex is easy. You look at port, switch port. You can look at it for you. Packet loss. LFN is easy. What's the round trip? What's the bandwidth delay product? All easy things. Okay? And use the information in the trace file to rule out some of the usual suspects. So what do I mean by that? So let's take a look at the trace. And again, number 3 here. MTU problems are common. MSS, are they common or not? What's the difference between MSS and MTU?
MSS is a MTU is IP.
Yeah, so MTU is the Ethernet concept, right? Ethernet drivers are worried about MTU, how big the Ethernet packet frame can be. I just caught myself, like that. Ethernet frames, TCP packets, right? And TCP doesn't care about the MTU, technically, although they do, but technically you don't have to know about it because you have the IP layer and they can fragment. Okay, fragmentation is equal to, but we'll get into that some other time. So, why don't I have a little packet thingy here? Because I couldn't use BitTwist to anonymize the IP headers because this one is not 1Q trunking. So if anybody knows a good IP changing program, please let me know. I use BitTwist and it works almost all the time, except this time it couldn't deal with this to that 1Q. Okay? And then I spent many hours by deleting that with a cat and then trying to change the 8100 to 0800. Okay, so what can we tell about this transfer? Give me some observations immediately. What kind of environment are we dealing with? Long fat network? LAN environment. How do we know it's a LAN environment? I'm sorry? That's right. The SYN-ACK is very, very close, right? So we cannot be dealing with a WAN network. So should you be worried about a long fat network? No. You just have a fat network. It's not long. Okay? We'll throw that out. Are you going to see a TCP Windows related problem in a LAN environment? Typically not. Again, it goes back to the motorcycle. If you only have to go short distance, using one person per payload is not that bad. Okay? So you can kind of throw out the TCP window analysis. You can kind of throw out the long fat network, right? What else? What are some of the other things that can happen? Retransmissions, etc., right? So, muscle memory, we do this. And what do I see? TCP Windows update. What's a TCP window update?
The reduction or increase in window advertisement.
Yes. Yeah. Should you see Windows updates in a normal transfer? Yeah. All it means is, what does it mean? Someone give me a quick, oh, I'm running out of time. What does it mean? What is this telling you? This is where you need to.
So the application cleans some stuff out of the buffer. So you got more space.
Okay, so who's doing it? The 162 guy, right? He's saying, look, I took this off my stack. I'm freeing up some more window size. Go ahead and use it. And there are 5 out of how many? 1,000? Not a big deal. You expect to see. Now, what is a problem is if your window size goes to 0 for a long time. That means you cannot receive any more data. That's a problem. Doing a Windows update saying my window just went up, you sent me a lot of data, I consumed it, my window size has not gone up, is okay. In fact, you almost want to see it because it's efficient use of resources. So what else is wrong? So let's start to scan, right? This is where you need to start picking up patterns, right? And anybody see anything here? Oh, here's a Windows update, right? I'm sorry, what did I hear? All the sequence numbers are even? Okay. I'm sorry, you got to speak up.
It looks like he's filling the receive buffer. You want to get a link to the client.
Okay, so the Windows update you're saying. Consuming a lot of data and saying, okay, all right, what else? And I'll go back to it can be easily seen. It's right there. If you look at it, you'll see it.
Vendors blasting away and then clients.
Okay, but don't formulate a problem. Don't formulate the answer yet. Just describe the problem. So don't jump to the answer. Describe what you're seeing because it will lead you to the answer. Okay, that's sound to meditation. But
TCP line is full, and then it fills it up that last buffer, and then you can find the problem.
I think you hit on the. So say that one more time.
Well, the TCP length is full up until it gets to that last 1354, and then that's filling the window.
Okay, you're very close. You're very close. You kind of got to the destination in a roundabout way, but you're very close. What do we see here?
The application sending a fixed length of data.
Application is sending a fixed amount of data, right? And it's fitting into an MTU. Perfect description. What else? In the next 30 seconds or so.
Then we see the axe come back and there's a stir of applause before the next block comes.
Yeah. Who said that just now? Okay, you can't speak anymore. You bet. So what's different here? Just tell me what's different. What's different is this. Look at this. This sticks out like a sore thumb, doesn't it? It doesn't do that? You guys don't see that? You see push act. Push act. And that push act happens to coincide with what? Nothing. I don't know. It's just an observation for now. Right? And what does a push typically do in the application world? Not the textbook answer, but in the application world, what does it do?
Force the packet to be sent.
I'm sorry?
Force the packet to be sent.
Forces the packet to be sent is how it ends up getting used, however incorrectly. What it tells you, right, is that the application is trying to dictate how much data it can send. And one way to do that is give it a big chunk of data, and oh, by the way, this is my last one. I want to set the push bit on it. Okay? And it kind of gives you, not always, but it kind of gives you an idea that there's a boundary of data being sent by the application, not by TCP. So it's not giving a bunch of data to TCP and saying, you do your job, you let me know. He's saying, here's a little bit of data. By the way, put a push bit on this one, because this is the last one. Okay? So it kind of gives you a boundary condition where, so is that wrong? Yeah, maybe. It depends on how efficient the application is, right? Because if application is doing flow control, TCP's flow control doesn't come into play. Okay? So remember, there's application level flow control, TCP level flow control. And if the application is smaller, TCP can never ramp up. So why is this important? Because this caught my eye, and I said, oh, application buffer tearing. Application is trying to dictate. When you do the analysis, it turns out, you see this delay here? Right? I'm seeing these ACKs come back. Boom, boom, boom. These are ACK trains, right? All these ACKs are coming back. And all of a sudden, I see a delay. Right here. Why? I mean, don't you want to know why? It's interesting, no? I mean, yeah, the packet traces are boring, but isn't this interesting? All of a sudden, you got all these ACKs coming. You got a slew of packet trains leaving the station, ACKs coming back, and all of a sudden, there's a delay in one ACK. Why? Because if you look at the sequence number, all these packets were being sent, except for this last guy. Okay? So let's do the analysis right here. So the next expected sequence number is 078. The next expected sequence number is 078. And that gets acknowledged right here, 078. I've now acknowledged up to this point. I'm all caught up to this point. Then what happens? An odd number of packet goes out. What does that mean? Can I acknowledge that immediately? No. The RFC says what? In layman's term, every other packet I can acknowledge. Okay? So long as I'm getting 2 packets, I can acknowledge it immediately. But if you send me just 1 packet, remember, we're all caught up to this point. I sent this packet out. I've only sent 1 packet out. I'm waiting. Why am I waiting? Because I have a push bit. Because the application won't give me any more to send out. This is all I got in my buffer. I send that out, but it's only 1 packet. The other side can't acknowledge it immediately because he says, I need every other packet. So it comes with a delay, Nagel, delayed ACK, deadlock. I can't send you anymore because I don't have anything to send in this case. But I can't acknowledge it either because you've only sent me 1 packet. I need to see 2 packets before I acknowledge it until a timer goes off, a delayed ACK timer. Then I acknowledge you, and then what happens? Then the next packet train goes. Okay, so this is how much the application is sending in one shot. Then we're going to see this pattern happen again and again. Everybody gets acknowledged except for that last packet. Okay, so in quickly, and I'll type up the answers in the presentation so you don't have to memorize everything. But the key point is this: when you first look at this trace, you're thinking, "Oh, this is beautiful, bulk transfer. I got nothing but large-sized packets going. I got a storm of ACKs coming back. This is exactly how a bulk transfer that's efficient should look like." Until you notice that push on that last packet, right? This looks different. The size is different. Immediately pick those out. You do the sequence analysis and realize it's the evil odd packet. Okay? If you're dealing with Microsoft SOAP, be aware of this because Microsoft SOAP stack tends to send out odd number of packets. And you'll get bit because you're going to get into this war of, I can't send you anymore because you haven't acknowledged me. I'm not going to acknowledge you because you haven't sent me 2 packets. And you go to a deadlock. Okay? I'm actually late for I actually overran. The next one is, I can't do it, but it'll be in the trace. It's looking at SAC selective ACK. So how Wireshark displays selective ACK fields for you, and how you can use it to analyze the throughput, and what it means to you as the person doing the analysis. Okay? Any questions about what I presented today? Just as a selling point, if you will, but not much of a selling point. In the advanced session, I go over some unique cases that's even more complicated and not run-of-the-mill. And also, I'll give you a spreadsheet that you can use to diff router configs. And it's an intelligent diff and spreadsheet that lines up interfaces and highlights key fields from fields that you care about. Right? Show like BGP sum, the prefixes are important, database sequence numbers are not important, things like that. Okay? So I'll give you that. It'll also be posted as part of the presentation. So that's it. Any questions? Okay, thank you for